Okay, Bismillahirrahmanirrahim. So in this video, we are going to go through series DC motors. A series DC motor is a DC motor whose field windings consist of a relatively few turns connected in series with the armature circuit. Or we can just simply say that a series DC motor is a DC motor whose field windings are connected in series with the armature circuit, which can be seen from the equivalent circuit diagram below here. Yeah? So you can see that here we've got our field circuit, yeah, which is in this pink box, is connected in series with the armature circuit, yeah, the circuit here. Okay. So then by using this equivalent circuit, then we can derive the equations that we can use to analyze this motor. From the KVL, we can see that Vt, yeah, is Vt equals to, if you like, the voltage drop across this, yeah, the series winding, and then the voltage drop across Ra, yeah, the armature resistance, and then plus this voltage Ea. Yeah. So again, Vt is equals to Ea plus the voltage drops across Ra, which is the armature current. The armature current into Ra. Yeah. Ia into Ra plus the voltage drop across the series resistance, which is Ia times Rs. Yeah, we could have written it as Is into Rs. Yeah, this is Is. Yeah. However, from the KCL, because this is only one single loop. Yeah, sorry, to undo that one. I don't know. Okay. So all the currents are the same, which is Ia equals to IL equals to Is. Is normally we call it field current. Yeah. It's just because now the field circuit is connected in series, so the notation used in this diagram is Is. S stands for series. Yeah. But I don't think it's a problem to still stick to If rather than using Is. Yeah. So these are the two equations that we can get. Hold on, if we go back to our KVL, this can be simplified into Vt equals to Ea plus Ia in brackets Ra plus Rs. Yeah, and again Ra is the armature resistance and Rs is the field or the series resistance. Yeah. Okay, now we'd like to see the characteristics of this series DC motor. Yeah, a series DC motor is very different from the shunt motor due to the fact that the flux is directly proportional to the armature current. The flux is normally have some proportionality to the field current, not the armature current, which can be seen from this magnetization curve. Yeah. This is, we've got flux here and we have MMF. MMF is actually N into IF. Yeah. So there is some, especially in the linear region here, this linear region, we can basically assume that the flux is directly proportional to IF. However, we have learned from the equivalent circuit that IA equals to IF, yeah, or IS if you like. These two referring to the same thing, yeah, which is the field current. Okay. So again, if I can repeat that in this series DC motor, the flux is not just directly proportional to the field current, but it also at the same time directly proportional to the armature current. Yeah? So as the load on the motor increases, the flux also increases. Yeah? And an increased flux will cause a decrease in motor speed that we can see from the equation that EA is equals to K flux omega. Yeah. So assuming everything else is constant, when the flux is increased, the omega will be decreased. Okay. Right. Now we would like to see what is the output characteristics of this motor like. What is the relation between the torque and the speed of this motor? Yeah. Okay, so we are going to derive the output characteristics of this motor. Okay, the flux is directly proportional to IA because IA equals to IF, and therefore the flux can be written as flux. Okay, bigger, and let me repeat again. Maybe I should use a thinner pen. Okay, so the flux is equal to C times IA. Yeah? And again, this is because the flux is directly proportional to IA. So we can write it down as this equation. Now the induced torque is given by K into flux into IA. Okay. Okay. Okay, and then we can substitute flux or pi. So we have induced torque equals to K substitute flux by C times IA into IA. So what we are going to have here, that the induced torque is equals to K times C times IA squared. Yeah. Okay, which is interesting equation that we have here, because we can see now that the induced torque of the motor is proportional to IA squared, which means that this motor actually gives motor per ampere that is higher. It gives more torque per ampere compared to other DC motor. So it has higher torque per ampere, which is a unique characteristic of this motor. Okay, to allow us to find the relation between the speed and the torque, Now we'd like to rearrange the above equation to solve for IA. So we can write that IA is actually equals to IA squared induced torque divided by K times C. And so IA, if I just rearrange slightly or just write it down as square root of induced torque over K times C. Just keep a bit. Okay, yeah. So that's IA equals to. Okay. Now to proceed, we are going to start to use the KVL equation, which is given by this equation. VT equals to EA plus IA times in brackets RA plus RS, yeah, which we've already seen previously. Okay, and I think I'd like to change the size of the pen. Okay, now we know that EA is equal to K pi omega m, okay, just the speed. Okay, so we can write this as K times pi times omega m, yeah. While IA, we are going to use this for IA. Okay, so this will be equal to square root of the induced torque over the K times C times RA plus RS. Okay, and how can we proceed from here? Now we are going to use other information, yeah, that the induced torque, yeah, again, if you induced torque here is equal to K times flux times IA, yeah, and then we can replace, because IA is equal to hold on, IA what we know that flux is equals to C times IA, yeah, you can check again the above to find this equation, and therefore we can write it down as K times pi squared over C. That's our induced torque. Okay, and then we can write it as, to solve for pi is equals to square root C over K times square root of the induced torque. Okay, now we are going to substitute this pi, if you look on the left, with what we have just found. Yeah, so we have now k into square root of c over k times the induced torque into omega m plus the induced torque over kc Ra plus Rs. And again, we still have Vt on the left here hand side of the equation. Okay, now what we are going to do? What we can do now is we take out the common factors. Yeah, the common factors, which is in this case, this will be this, and then this one here. Yeah. So we take this out. The induced torque, the square root of the induced torque over square root of k times into bracket k square root of c times omega m plus Ra plus Rs over square root of c. Okay, and then I'll move this bit to the left hand side of the equation. So we are going, we have square root of k divided by square root of induced torque into Vt equals to k square root of c omega m plus so we can solve this for omega m. Square root of k So what do we have in here? Omega m equals to Vt divided by square root of k c induced torque minus Ra plus Rs over kc. Yeah. So this is our equation for the that show us the output characteristics of this. And if you see this equation here, give us the relation between the speed and the induced torque. So note that the speed is proportional to the reciprocal of the square root of the torque, yeah? Which is interesting, because if you then plot this equation, this is what you're going to have. Yeah? Yeah. This is to plot of the speed versus the induced torque. So as the induced torque is getting larger and larger, the speed is getting less and less. However, as the torque is getting less, when the torque is approaching zero, the speed of the motor getting higher and higher is going towards infinity. Because you can see from this equation, if the induced torque is zero, 1 over 0 will give you infinity, which means that the speed of the motor will be very, very high. Okay, so this is disadvantage of this motor, that when the torque goes to 0, the speed goes to infinity. So what we learn from this is that never completely unload a series motor, and we should avoid never completely unload a series motor, and we should avoid to connect a series DC motor to a load by a belt or other mechanism that could break, because if the belt of this mechanism breaks, the load becomes zero, if you like, and therefore the motor will the speed of the motor will keep increasing towards infinity, which will then be very likely going to damage the motor. Okay, so again, that is the speed characteristic of the motor. Okay, and then finally, how do we control the speed of the motor? The speed of this series DC motor can be controlled by two methods basically. So first, by changing the terminal voltage VT, okay, and this is the only efficient way. Or secondly, by inserting series resistor into the motor, but this is very inefficient, because if you go back to the equivalent circuit of this motor, okay, so if we add a resistor in series here, to enable us to change the magnetic field, the current that goes through this resistor can be very high, because now it's not only the field current but also the armature current will flow through this additional resistor, and because the armature current depends on the load, and when the load is high, the IA will also be high, and therefore your I squared R losses will be high as well. So this method is not preferred for this type of motor especially. Okay, so I think that's all that we'd like to cover for this series DC motor. Thank you.